In Chapter 5, Section 1, we are going to be discussing how populations grow. One of the main questions we're going to answer is, how do ecologists study patterns? Well, the way that they study patterns is by using a population's geographic range, their density and distribution, their growth rate, and their age structure. We're going to learn what each of those are. Let's quickly define population. Remember that a population is a group of individuals of the same species that live in the same place at the same time. The geographic range is one of the ways to study populations. This is an area that is inhabited by the population. That's called its geographic range. A population's range can vary enormously in size depending on the species. Population density refers to the number of individuals per unit area. Populations of different species have very different densities, even in the same environment. A population of ducks in a pond, for example, might have a low density, while the fish and other animals in the same pond can have much higher densities. Distribution refers to how individuals of a population are spaced out. Some of them are randomly spaced, some uniformly, and some can be concentrated into clumps. This is an example of random distribution. It shows you how some wildflowers are just randomly spaced in a certain area. This example shows a more uniform distribution, where each organism has a certain amount of space to themselves, and it's pretty much the same amount of space as each of the other organisms. And finally, this shows those that are in clumps. A lot of times we're talking about organisms that would travel in herds or in schools, like these fish. A population's growth rate determines whether the population size is increasing, decreasing, or staying the same. This, for example, is a population of deer, and they are definitely growing. We also have to discuss age structure when we're talking about populations and their growth. Age structure is the number of males and females of each age a population contains. Most plants and animals cannot reproduce until they reach a certain age, so it helps us to give predictions about the next generation. And we also need to remember that only females can produce offspring when we're discussing animals. Now we're going to talk about what factors can affect population growth. We're going to talk about birth rate, death rate, and even the rate at which individuals enter or leave the population. A population can increase or decrease in size depending on how many individuals are added or removed from it. The factors that can affect it are the ones we just discussed: birth rate, death rate, and then immigration and emigration, which is the rate at which individuals enter and leave. If a population's birth rate is higher than its death rate, then you're going to get an increase in population size. If the birth rate equals the death rate, the population may stay the same. But if the death rate is greater, you're going to have a population that will shrink. Populations can also grow from immigration, which is the movement of organisms into a population. But emigration can cause populations to decrease due to the exiting of organisms from a population. One type of growth to discuss is exponential growth. So we're going to learn about what happens during exponential growth. And under ideal conditions with unlimited resources, a population can grow exponentially. If you provide a population with all the food and space it needs, if you protect it from predators and disease, and remove its waste products, the population will grow. The population will increase because the members are able to produce offspring. And after a time, those offspring will then produce their own offspring. Under ideal conditions, with unlimited resources, a population can grow exponentially. In exponential growth, the larger a population gets, the faster it grows. The size of each generation of offspring will be larger than the generation before it. Whenever you plot the numbers of organisms that are growing exponentially, you get what is called a J-shaped curve. It's one that will rise slowly at first, but then begins to rise faster and faster. In this example here, we're growing some bacteria, and you're seeing that the population slowly grows, but once it takes off, you can't stop it. It gets larger and larger and faster until it approached an infinitely large size. Now we've discussed exponential growth, let's talk a little bit about logistic. Logistic growth occurs when a population's growth slows and then stops following a period of exponential growth. Natural populations do not grow exponentially for long. Sooner or later, something stops that exponential growth. Let's talk for a little bit about what happens. So we're going to look at this graph down here, and we're going to suppose that we're putting a few individuals into a real-world environment. After a short period of time, the population will begin to grow exponentially. During this phase, the resources are unlimited, so the individuals can grow and, more importantly, reproduce quickly. Some of the individuals will die, but many offspring are produced, so both the population size and the growth rate increases more and more rapidly. In the real world, exponential growth does not continue for long for populations. At some point, the rate of population growth begins to slow down. The population still grows, but the rate of growth is slowed down, so the population increases less quickly. At some point, the rate of the population growth actually drops to zero, and the size of the population levels off. Under some conditions, the population will remain at or near this size indefinitely. Logistic growth is then different than just the J-shaped curve of exponential growth. It actually begins to slow down, and the population size may remain the same for long periods of time. It then has an S-shaped curve. Population growth may slow for several reasons. Growth may slow if the birth rate decreases or the death rate increases, or if births and deaths fall and rise together. In addition, population growth may slow if the rate of immigration decreases or if emigration increases. When birth rate and death rate are the same, and when immigration equals emigration, population growth will stop. There is a dotted horizontal line through the top region of this graph where the population size will level off. This point is what represents the carrying capacity of a population. Carrying capacity is the maximum number of individuals of a particular species that a certain environment can support. Once a population reaches this carrying capacity, a variety of factors act to stabilize it. For a quick review, remember what we talked about in this section was ways to describe a population, including its geographic range, its density and distribution, its growth rate, and its age structure. We talked in this section about population growth and the factors that affect it, like birth and death rates, immigration, which is organisms moving in to a population, and emigration, organisms exiting a population. We also talked about exponential and logistic growth. Remember, those organisms that reproduce rapidly show exponential growth, and those that grow a little slower will have logistic growth, which has the S-shaped curve, and exponential is the J-shaped curve.